Hello, my name is Ethan Vanderloo, and this is my final presentation for AERO 4842 for my device called the Cryo-vision. The mission objective is to develop a scientific instrument that would be used in a mission to Jupiter's moon, Europa. My design focuses on an onboard image recognition system that helps the satellite detect surfaces and nearby objects, enhancing its situational awareness, and it also assisting in maneuvers involved in landing and object avoidance. To achieve this design, the system must be capable of machine learning. This will involve an onboard AI that can autonomously analyze visual data and adapt it to Europa's environment. In turn, the system should be able to detect and classify surface features, ice fractures, and potential landing zones without relying on constant Earth communication. To do this, my design will require a computer-trained model that will be capable of interpreting terrain textures, lighting variations, and surface hazards, all under low light and radiation conditions. This will involve adding a camera to sense and capture objects in frame. The camera will be able to continuously capture images of Europa's surface, feeding them to onboard machine learning system for real-time recognition and mapping. So what is image recognition? It's essentially a form of computer vision, the ability for a computer to see and understand visual information. Using machine learning and deep neural networks, same as a human brain, where the system can identify and classify objects in images or video. The computer will be trained on a large data set containing thousands or even millions of images. From this data, it learns to analyze pixel patterns and recognize visual features, like shapes, textures, or even motion. So the process. First, we must capture the image. This is by using a camera or sensor on board the system. Next, we must pre-process this image. This is the data preparation stage, where the raw images are cleaned, adjusted, and standardized before analysis. During this process, lighting variations, for example, from Jupiter's reflected light on Europa's mission, can be normalized. Noise by cosmic radiation is also filtered out to make the image clearer. We can now detect and classify objects. This is done by the neural network, which analyzes the processed image and identifies specific objects or patterns. After these objects and patterns are recognized, the results are now outputted. This can include labels, bounding boxes, like as you see in the images, or automated control actions based on what the system detects. The main parts of my design is first the Raspberry Pi 5, which is used as the brain that contains the neural network, enabling the image recognition. Next is the camera module with a sensor, which the module takes an image or video, while the IoT relay will control the power, essentially acting as a breaker, and can be used in other applications. For example, if an asteroid is detected in the mission's path, the relay could switch on the power to the thrusters, generating a maneuver out of the asteroid's path. Likewise, the relay would be able to initiate the landing gear when the surface of Europa comes into vision. As mentioned, the system functions as an automated image platform, controlled entirely by the Raspberry Pi 5, as seen on the left. The Pi runs the interface code and manages hardware through its GPIO pins. When an image capture cycle begins, the Pi sends a high signal on the GPIO 14, activating an IoT power relay. This closes the relay's internal switch and powers the lamp from the wall outlet. With the lamp illuminated, the camera module connected to the Pi through the CSI port captures a well-lit image for analysis. The Pi can pre-process these images and run the software detection locally, enabling real-time decision-making. Once imaging is complete, the GPIO 14 is set to low, turning the lamp off and conserving power. In practical applications, similar architectures are used for ice-penetrating probes, autonomous landers, and surface monitoring stations, where controlled illumination and onboard image processing are essential for detecting environmental changes, identifying hazards, or characterizing terrain. The Raspberry Pi relay camera setup demonstrates these same principles at a smaller scale: local decision-making, adaptive imaging conditions, and power-efficient operation. Now I will show you a live demonstration. Here are the main parts of my apparatus: the Raspberry Pi, the Pi camera, the IoT relay, which is connected to the lamp. As you can see on the Raspberry Pi screen, there is a border outlining me called person, a yellow box, and a black dot. The black dot is the center of the frame, which depicts that the software has recognized me as a person. Once the black dot is encapsulated within the yellow rectangle, the code will prompt the Raspberry Pi to provide AC current to the relay, turning on the lamp. In this video, you can see how it works. As soon as I step into the yellow frame, the light will turn on. And as soon as I step out, the light will turn off. In this video, I demonstrate that a different object can be put into the yellow frame as well. As you see, it does not turn on the lamp. But as soon as I walk into the frame, the lamp will turn on. This is because the software will only illuminate the light when a person walks into the frame, demonstrating that the software will be able to complete a specific task dependent on what is seen. The software has a couple key steps. First, it must validate the input. The input in this scenario is the Pi camera. Next, it must load a YOLO model. A YOLO model is a large database of images on which my Raspberry Pi is trained on. The software then sets up the display/recording parameters, such as the resolution if specified, then initializing the source. So if you are importing images, instead of taking a video, these images will be uploaded and then run through the code. This code runs on a main interference loop. So first it reads frames from the source. It resizes the frames if needed. It then runs the YOLO interference. This is so we can detect those objects. Then it draws bounding boxes and labels for the objects, which has been from the YOLO database. Then it displays frames with FPS, the object count, and frame info. And then it optionally records the video. And finally, it runs a cleanup in releasing this video/camera resources, stops the Pi camera, closes the window, releases the recorder, and prints any summary statistics. Real-life applications of my apparatus would be asteroid and space debris detection/tracking, precision landing for planetary exploration. This is including hazard detection and obstacle avoidance, as well as surface feature identification, so mapping ice fractures or terrain, and monitoring of mechanical systems or instruments through onboard cameras.